Hey guys, how's it going? Make sure all the things are set up so it'll work today. Hope you guys are not freezing to death. It's quite chilly in Jacksonville. This morning when I walked the dog, there was frost. And I was like, that's a lot. So, hope you guys are doing well, hanging in there. Today is our last session. I can see that nobody's here yet, so we'll give you guys a couple seconds to get around so that we can all get things together. But then we'll give some info about the final, and then we will go from there. Sweet. Hey, how are you guys today? I'm glad you're here. I never thought this semester was going to end. One of my friends was talking about something that happened months ago, and I was like, no, that was like 3 years ago, right? No, it was in September. I just forgot. So, glad you guys could all make it today. We'll give you guys just another second or two to kind of arrive, get your life together. Then we will give some brief announcements. I mean, not really announcements, info that will also come on Friday, but you may have questions about the final. Then we will get to the chapter 10 material. So, I feel the same way about this semester. Not gonna lie. So let's talk about the final exam. On Monday at 3 p.m., your final will open the exact same way everything else has on Canvas. A little bit early in case you're like nervous. I like to know what's happening in advance. So the final will open. It will have a 300-point exam that will be open from 3 to 4:50. Now you may be like, oh, that's great. I could start late. So at UNF, our final exams are longer than our class period. So you get 1 hour and 50 minutes, which is approximately, I think, 110 minutes, and your exams have just been 75. So you get a little bit longer. It'll be worth more points. It will be, I don't want to say the exact, it's not the same, but it will be a series of low point questions, high point questions, math questions, I don't want to say counting questions, but questions like that. You will submit that. It will probably take me most of the week to get those graded. When they are graded, they will upload for you to give it any last look-sees before your letter grades are posted. The letter grade that you see in Canvas is the letter grade that you have right now. So when all of that is upgraded, your ALEKS scores will go in probably next Monday so that you guys can keep an eye on that kind of stuff. I mean, that's not really going to change. So I'm going to talk about ALEKS. If you have any questions about the final, you can go ahead and You can drop those in the chat box. ALEKS. So I've gotten a couple of questions. The on-time score, you can see that in the grade book. If you turn them in on time, and you know if you have, then it doesn't matter if it takes them away. Now, the other part, so that's worth 100 points. The other 100 points of your homework is for completing your PI. So let's say you take the knowledge check, and there's one this week. Let's say you take that knowledge check. Then what happens? So ALEKS may give you or take away some objectives, but then during the open PI period, you can basically go through and redo anything else. There are no more knowledge checks after that, okay? David, I hope so. I miss having my students live and in person. I miss hearing you guys laugh at my terrible jokes and all the rest of that. So a little bit longer. So does anyone have any questions about either the final or ALEKS before we look at chapter 10? and or anything else. Ooh, while you're dropping those, office hours. I will have office hours. They're on Zoom on Friday from 10 to 12. I think I will try to send you guys a link in an announcement Friday morning right when they start. So if you're like, I don't even know how to get there, that's where they are. I will also, in the Friday announcement, they'll be separate than that. We'll tell you when I think I'll have office hours on Monday at a different time. Ooh, we got some good Alex questions. So could y'all ask, the chapter 10 Alex is due on Friday? Yes, I'll double check that. It's supposed to end on Friday to give you guys some more open pie period, but it won't affect your ability to do those. So if you miss that deadline, just do it during the open pie period. So the open pie period should start on Saturday morning. I will verify that. Do I have a pen? I don't have any paper, so I'm just going to write on my hand. I'll double check that. And then Avery asked, do we have to master everything or just learn it? So the mastery, where it goes from light blue to dark blue, only happens with a knowledge check. So you need it to be a color of blue to get credit for it. If it is grayed out, you will not get credit. If it's not grayed out, light blue or dark blue, that counts. Nicole state/ask a question. Open pie period starts after you finish the chapter 10 objectives. That is definitely true. And then Jordan asked, do you get +5 for writing your name on every page? Jordan, I assume that you are asking about the final, and that is definitely true. If you're asking about something else, there's nothing else you could be asking about. That's silly. Yes, if you write your name on every page of your work on the final, you will get 5 bonus points. Mariah double checked. And Jordan asks, will Graham's law of effusion be on the final? So that's a great question, Jordan. It turns out in this class, we are only going to look at the first 2/3 of chapter 10. So I think my videos end with 10.6, which is partial pressures. So that is the end of what we will discuss. So Graham's law of effusion and diffusion and the kinetics of gases and the van der Waals equation, we will not talk about, and they will not be on the final. There you go. Looks like people are answering your questions, Miss J. But what I said was the Alex, so there's a status bar at the top that's like dark blue, light blue, and then gray. You need that thing to be all a color of blue. Any other questions today before we, and you know what, if something comes to you, just drop it in the chat box. We'll get to it. Otherwise, we'll start with chapter 10. We have 9 questions today. So, awesome. I'm going to go ahead and get that moving. So, our first question today is, a hurricane has a pressure of 947 millibar. What is the pressure in torr and in atmospheres? Jordan, you just asked, is that covered in Gen Chem 2? I think so. But I am not entirely confident as to what happens in Gen Chem 2. I have never taught that class. But I think they will talk a little bit more about that in Gen Chem 2, I think. So for question 1, video, we have our 947 millibar. Now in the 10.1 video, there is a list of unit conversions. That's all this is. Pressure comes in like 1 of 900 units, depending on what type of scientist you are. Do you care about gas tank pressure, like in a tank because you scuba dive? That comes in PSI. Do you care about the hurricane pressure? That's usually in millibar. If you want to talk about atmospheric pressure, sometimes they use torr. Pressure has 100 different units, and we can convert between those using the values. I will upload the final equation sheet, which will have all of that information in any of those values. It's also in the slides, but I will upload that tonight. So there are 1,000 millibar in 1 bar, and there is 1.01325 bar in 760 torr. When you plug this into your calculator, you should get 710 torr. So don't forget sig figs. We got to remember those. Significant figures are based on the starting part, and so 947 has 3. You could have changed this into scientific notation. I just didn't. So it also asks for it in atmospheres, which you could have done one of 2 ways. You can take your 710 torr multiplied by 760 torr in 1 atmosphere, or you can take your 947 millibar. There are 1,000 millibar in 1 bar. And there are 101,325 bar in 1 atmosphere. Regardless of how you plug this into your calculator, you should get 0.935 atmospheres. So this is just a traditional, and I'll move out of the way, unit conversion question. So do we have any questions about number 1? If you don't, as always, drop none in that comment box, and we'll move right along to question 2, which I will. Okay, all that. We'll just put that right here. So, all right, make that go away. Any questions, any thoughts, any confusions about pretty typical unit conversions? I like it when it's a bunch of nuns. Makes me super happy. So question 2, quite pandemic appropriate. A 450 ml Lysol spray can contains 0.143 moles of Lysol. The chemical compound Lysol is a real thing. It is irrelevant for the purposes of this. If the can is stored in my office at 26.1 degrees Celsius, what is the pressure inside the can? So this is a PV equals nRT question. So we know we're going to use PV equals nRT. So the question is, what do we do with this information? My preferred method of how do I approach this? So if I know what question I need, or equation, I write it down. On the other side of the blank space, I tend to write down what I know, because if I don't know what equation to use, it gives me a hope. So we know that we're looking for pressure, question mark. Our volume is 450 milliliters. There are 1,000 milliliters in 1 liter, which gives us 0.450 liters. N equals 1.134 moles. And I'm going to use R of 0.0826 liters, atmospheres, mole, Kelvin. So now we're going to plug it in. So we know we're looking for pressure. P equals nRT over V. Now we're just going to plug in these values. Whoa, JK. Temperature, notice we're getting something, is 26.1 degrees Celsius plus 273.15 gives us 299.25 Kelvin. So it is 0.134 mole multiplied by R, which is 0.08206 liters, atmospheres, mole, Kelvin, and then 299.25 Kelvin, divided by the volume, which is 0.450 liters. When you plug this in, you should get, hopefully, 7.312 atmospheres, which using our sig figs from the problem, which is just 3, I get 7.31 atmospheres. So what questions do we have? Try not to stand directly in front of all the work that you hopefully can see. So what questions do we have about this problem? What questions do we have, if you have any, about PV equals nRT? As always, if you don't have any, you can drop it over in that comment box or below. I don't actually know where the comment box is on your screen. So is this easy? Is it simple? How do we feel about this? Nice. So Ms. J asks, how do we know which R value to use? So there's two things you can do, to be honest. One, I almost always use the same one. The only time you don't need to, you can pick. So there's a list in the chapter 10 slides of the different values. So if your volume was provided in a different unit, you could either convert it to liters to use this R value or something else. The pressure, if I ask for it in torr, one of the values gives you that, or you could convert. Sweet. All right. Question number 3. Yikes. Struggle. Okay, a reaction occurs in a sealed vessel with a volume of 10.2 liters. Okay, sorry y'all. It's like I've never done this before. And there are 64.1, it's at 64.1 degrees Celsius, and 8.2 grams of nitrous oxide are produced. What is the pressure of NO in the vessel after? I'd like to apologize because I read all of these the other day, and I guess I didn't read them because we're going to solve for pressure 100 times. You could have solved for the number of moles or grams or other things, but apparently I asked you to solve for pressure only. Hopefully on the exam it's not the same, but the math works out the same every time. Okay, so I'm going to go ahead and leave that part up because we're going to use it again. Okay, so as we read the problem, we can see that the volume is equal to 10.2 liters. It gives us a temperature of 64.1 degrees Celsius plus 273.15 gives us 337.25 Kelvin. So now we need to solve for N. if you are forgetting how to solve for n from grams, we're just going to use the molecular weight. So we're going to take our 8.12 grams of NO, divide by the molecular weight, which is determined by adding the weights in the periodic table of 30.01 grams, and that's going to give us 0.271 moles. So now we can plug this all back into our equation of 0.271, whoops, forgot my units, moles, 0.08206 liters, atmospheres, mole, Kelvin, 337.25 Kelvin, and that is 0.271. Nope. It is in fact 10.2 liters. And so when we plug this in, we should get 0.735 atmospheres. So Ori, I think that's how you say that, asks, why do you convert the temperature into Kelvin? So with PV equals nRT, the R values require the use of Kelvin. Unlike chapter 5, where we were calculating delta T, which is basically temperature 1 minus 2 or 2 minus 1. So in this case, you have to convert to Kelvin every time. No matter what, in this chapter, you need to convert. There are some examples where it feels like we could get away with not doing that here in a little bit. Those are always going to mess up. And Jeremy gives our units. Good answer. Any questions about this calculation that I've now stood in front of? Any questions about how to determine the number of moles? Anything else? And really, any questions at all? I wonder if I rounded incorrectly. Entirely possible. I get 0.735. I found so it looks like Jordan and Nicole got 0.734. I found out where the difference is. It's always nice to bring a calculator. So if you divided this by this and used a longer version of this value, so like 0.2705764, some longer version of that, or the whole thing, in this calculation, it will give you 0.734 instead of 0.735. On the exam and on the weekly assignment, we usually give some sort of I don't want to call it a buffer. But if you've done all of this work and you're off by just a little, I usually should accept it. Nice. I like it when you guys are all bringing it together. Either way, it looks like you guys are figuring it out. So any other questions about this in this question? Otherwise, we will work on number 4. I think I answered this. We'll go ahead and hide this. Bring up the next. So this question says, an inflated balloon has a volume of 6 liters at sea level, 1 atmosphere. The balloon ascends, fancy word for goes up, until the pressure is 0.45 atmosphere. The temperature changes from 22 to negative 21, so 22 is at the ground, negative 21 is in the air. What is the volume of the balloon at the final altitude? So this equation is a manipulation of the ideal gas law, where because this is the same balloon, so we know that the number of moles inside won't change. But we also know that we're going from environment 1 to 2, so P1 V1 over T1 equals P2 V2 over T2. Now, what you assign as 1 or 2 is not irrelevant, but less important. It is important as to which one, as long as the 1s go together, or the 2s. So P1 is 1.0 atmosphere, V1 equals 6.0 liters, T1 is 22 plus 273.15, which gives us 295.15 Kelvin. P2 is 0.45 atmospheres. V2 is what I want to know. And T2 is negative 21 plus 273.15 gives me 252.15 Kelvin. So now we can plug these values in. 1 atmosphere multiplied by 6.0 liters divided by 295.15 Kelvin equals 0.45 atmospheres V2 divided by 252.15 Kelvin. So this is going to give us 11.39 liters. Sig figs are going to make that into 11 liters. What questions do you guys have about this one? In a second, I'm going to redo that calculation. Good Lord. Can y'all even see what I'm writing on the board? Sorry, it's the end of the semester and all my markers have died. So let's try that a little bit better. See if that helps. So let's do this calculation if we had left the temperatures alone. So if we just calculated with 22 and negative 21, let's see what we would have gotten. 6 divided by 20. 6 divided by 22. I would have gotten that in this case, with those values, I would have gotten negative 12. That the volume would have equaled negative 13 liters. And so that basically would have meant that that doesn't exist. Can we see the cross multiplication? Sure. So let's see. Where can I'll set it up over here. So when you calculate this, there are two schools of thought. You can either plug in this value and then this, but what I plugged into my calculator was 1 atmosphere multiplied by 6.0 liters multiplied by 252.15 Kelvin divided by 0.45 atmospheres and 295.15 Kelvin. So these are P1, V1, T2, T1, and P2. Okay, well, let's just see. I think that helps. Does that, it looks like Mariah said that worked out for her. Kajal, does this help your cross multiplication question, or do you have another one? Not a problem. All right. I'd like to apologize if the wiggly wiggles is making it a little hard to focus. So our next question asks us to calculate the density of SF4 at 25 degrees Celsius and 1.012 atmospheres. So let me get some board space going on. Where are my notes? So this uses a different version of PV equals nRT. So to calculate the density of a gas, which our book annotates as like a scripty D, which I've tried to do in the videos. So D equals the pressure times the molar mass divided by RT. So we know in this case the pressure, and that's 1.012 atmospheres. The temperature, we get 25.1 degrees Celsius plus 273.15 gets me 298.25 Kelvin. Now we need the script EM. I've almost always replied to that as the molecular weight. We don't tend to think about the molar mass, but we can. That's all it's asking for, which in this case is just the sum of the atomic weights. And I got 108.07 grams per mole. So now we can plug this in as 1.012 atmospheres multiplied by 108.07 grams per mole divided by R, which is 0.08206 liters, atmospheres, mole, Kelvin. And our temperature is 298.25 Kelvin. So from here, it doesn't really feel like these units are going to do what we're asking. So we know that the atmospheres cancel, the Kelvins cancel, the moles cancel, and so we end up with a value of 4.47 grams per liter, which, that's weird. Which are density units for air. So to calculate the density of air is a relatively simple calculation. It's very simple. It is similar to the calculation of density for anything else where it's grams divided by volume or mass divided by volume. What questions do you guys have about calculating the density of air? And as always, if you don't have any, let me know that too. Great. Thanks for letting me know, Nicole and Kinjal. Good. Nice. Whoa. So now this one is what I would consider a little bit more complex. It's not just PV equals nRT. So it says pure hydrogen gas is produced when zinc solid interacts with sulfuric acid. What is the pressure of hydrogen gas produced when 12.34 grams of zinc is mixed with excess sulfuric acid at 34.1 degrees Celsius? And the gas is collected in a 312 ml balloon. And then we have a balanced chemical equation over here. You could imagine that I might, give you an unbalanced equation to make you do that too. I think the final exam is a great place for us to start to mix together the material that you've learned from exam 1 with what we learned for chapter 5 and chapter 10. So, just so you know, I need this page. So we, in a non-surprising twist, are looking for the pressure. The volume of this is 0.312 liters, and I got that by our 312 mil divided by 1,000 milliliters in 1 liter. The temperature is 34.1 degrees Celsius plus 273.15 Kelvin, which gives us 307.25. N equals question mark. So, what do we do now? We're going to remember back to chapter 3. So chapter 3, if you vaguely remember, and hopefully if you don't remember today, it's a good mini refresher. So we can take the grams of a product, a reactant, and convert that to product. That's what we're going to do. So we're going to start with our 21.34 grams of zinc. We're going to then divide by the molecular weight of zinc, which is 65.38 grams and 1 mole of zinc. Then we're going to use the stoichiometric ratio. If you're like, oh my God, I don't remember that. The stoichiometric ratio are the big numbers in front of any compound in a balanced equation. So in this equation up here, there is 1 mole of zinc for every 1 mole of H2 produced. So when you plug this in, you can determine that 0.3264 moles of zinc are produced. Now we can just do the same calculation we started doing, PV equals nRT, or P equals nRT over V, which is going to be our 0.3264 moles. Whoops, that should be of hydrogen. Times our R, which is 0.08206 liters, atmospheres, mole, Kelvin, times our temperature of 307.25 Kelvin, divided by 0.312 liters. And this gives us a value of 26.4 atmospheres. Although if you did not round any of these values the same way, you will get something similar, hopefully, but not the exact same. So what questions do we have about this calculation? And as always, if you don't have any, let me know that too. Thanks, Angela. Nicole, thanks for letting me know. So far, chapter 10 is pretty easy, right? I mean, I feel like it's easy. It's easier than some of the others. Sweet. So, our next question says that an Arctic weather balloon is filled with 20.4 liters of helium gas inside a prep shed. The temperature inside the shed is, no one can read that because it's on the line, 15 degrees Celsius. The balloon is then taken outside where it's cooler. What is the volume of the balloon at 6.2 degrees Celsius? So this question, deceptively simple, right? So we are going to use that V1 over T1 equals V2 over T2. We are assuming that the pressure and the moles are entirely constant. So we know that V1 equals 20.4 liters. T1 is 15 degrees Celsius, which is 288.15 Kelvin. V2 is what we'd like to know. T2 is 6.2 degrees Celsius, which is 279.35 Kelvin. So we can plug this in, which is 20.4 liters divided by 288.15 Kelvin, V2 over T2, which is 279.35 Kelvin. To rearrange that to get V2 by itself, that would be 20.4 liters multiplied by 279.35 Kelvin divided by 288.15 Kelvin. And that answer is 19.8 liters, which I actually believe has one too many sig fig, and it definitely does. So with sig figs, that's going to give us 20 decimal point liters. How do we feel about this question? If you have questions, let me know. So the next two questions today deal with partial pressures. So do you have any other questions before we move on with the ideal gas law, the gas constants, any of the laws, Boyle's law, Avogadro's law, Charles's law, any of the other questions really before we get into the last part of this section? Mariah asks, what is the name of that gas law? This would be Charles's law, I believe. You can also find this, I tend to not think about these as part of the laws, but I believe this is part of Charles's law. Yes, because Boyle's is pressure and volume, Charles is volume and temperature. Good. Yeah, I'll be honest, I feel like this chapter is all very straightforward, here's this equation, do this calculation. It's a little bit less manipulations. Although we all know that Alex is going to give you some interesting things to make you do that. Good. I'm glad that answered your question. So our next question says, a mixture of 0.341 moles of argon, 0.832 moles of krypton, and 0.512 moles of xenon are contained within a 14.2 liter tank. If the total pressure within the tank is 980.1 torr, what is the partial pressure of each gas? So in this case, it gives you a volume. And it feels like you should be able to total up all those moles and calculate using PV equals nRT P total. Or, well, it gives you P total. So I don't know what you would calculate, I guess for temperature. In this case, we're going to use the partial pressure equation that P1 equals Chi1 times P total. Chi1 is the moles divided by total moles. So in this case, we know the moles of each one, but we need to determine the total moles. Now, some of you might have been like, oh, those are just the mole fractions. It will say mole percent or mole fraction if that's what you're looking for. Each of those do not total up to 1, so they can't be the mole fraction. So in total is equal to 341 plus 0.382 plus 5.512, which gives us 1.235 moles. So the pressure of argon is 0.341 divided by 1.235 multiplied by 980.1 torr, which equals 271 torr. The moles only have 3 significant figures, so we're curving it back at 3. The pressure of krypton is 0.382 divided by 1.235, 980.1 torr, and that gives us 303 torr. And the partial pressure of xenon can be calculated also using this calculation, or you could subtract from 980 the other 2 values, 0.512 divided by 1.235 times 980.1 gives you 406 torr. Now in this case, because I like to test, make sure I did it right. These 3 values should add up to the total pressure. If you do that, you get 980, but the 0.1 is missing. There's not a lot we can do for that due to sig figs, but it should be fine. So what questions do you guys have about this part of partial pressures versus any other part of partial pressures? Nicole asks, if the question gives torr for the pressure, would it be wrong to convert and report partial pressures in atmospheres? Absolutely not. If in this one it did not specify, and I wrote this question, so when I say hopefully on the exam, it won't. But if it doesn't tell you, you can put it in any units you like. So it would not be wrong. It would only be wrong if it asked for it, if it gave it in torr and then asked for it in atmospheres. But will we get a question that doesn't give us the moles? Yeah, number 9 will give you grams of each, and then we'll go from there. Mariah, if you're asking, if you printed out the questions and you're asking about the next one, let's do this a different way. If the next question isn't what you're asking, if you're asking for a different type of mole value, let me know. Any other questions about question number 8? Okay, so number 9 asks, a 9.34 liter vessel contains 32.12 grams of propane, and no one can read that, but it says 16.12 grams of argon. If the tank is stored outside at 39.1 degrees Celsius, what is the partial pressure of each gas? The mole fraction of each gas and the total pressure. Before we answer that, Catherine asked a good question, and so the answer to Catherine's question is the volume of the tank is irrelevant. You don't need that information. It was just kind of there to kind of like, I don't say throw you off, but it was an outlier. So Ms. J asks, which part is the mole fraction? Yes, so mole fractions. So Chi1 is the mole fraction. And a mole fraction is the moles of A divided by the total, that's like not a word, by the total moles. So you either see this as a mole fraction, which in this hypothetical situation would be 0.241 mole fraction, or you can see 24.1% by moles, or some other version like that. That's where you would see the mole fractions. Does that answer your question before we move back to, does that answer your question? So in this next question, it asks us to determine the mole fraction, the partial pressure, and the total pressure. So Mariah asked, do the individual moles have to add up to 1? The moles don't, the mole fractions do. So there's a difference. The number of moles do not have to add up to 1, because you could start with 3 moles, 4 moles, and 8 moles, and still have a mole fraction of those values. So the fractions have to add up to 1, because it's basically like what percent of the stuff in the tank comes from anything else. Good questions. So I'm going to make a little table over here. So for propane, which is one of the compounds you had to memorize, and you're like, oh my gosh, I've never heard of this before. That's okay. It's C3H8, and the other one is argon. So we need to determine N, Chi1, or Chi, and the pressure. We also need N total and P total. So how you go about finding these values, you can do a number of different things. I'm going to show you a method. If you've gone to SI, Megan may have shown you, or will show you, hard to say, a different method. You should get, within a very slight error, the same value of both of these, regardless of how you get there. So the first thing I'm going to do is calculate the moles and the mole fraction. So for propane, I'm going to take my 32.12 grams. There are 44.11 grams in 1 mole, and that gives us 0.728 moles. For argon, we're going to take our 16.12 grams divided by the molar mass of 39.1 grams in 1 mole of argon. And that's going to give us 0.403 moles. So we can transfer these to our table. 0.728, 0.403. So in total is going to be 0.728 plus 0.403, which is 1.131. Okay, you can still see that. So to calculate chi, it's going to be N over N total. So these values are, let's calculate these over here. So chi of C3H8 and chi of argon are 0.728 divided by 1.131, 0.644.35. Whoops, that's the wrong value. 0.403 divided by 1.131, and that gives us 0.356. So from here, there are 2 different ways you can do this. You can either use in total to calculate the total pressure and then use the partial pressure equation to calculate the partial pressure, or you can use PV equals nRT for both of these values and set it up. I'm going to use the total number of moles, and I'm going to try to find a space for that. We'll erase this. It can come back if needed. So I'm going to determine that P total is equal to nRT or N total over V. And so based on the problem, we know that the volume is 9.34 liters. N total is 1.131 and T is 39.1 plus 273.15, which gives me 312.25 Kelvin. So we can plug this in over here. 1.131 moles divided by 0.08206 liters, atmospheres, moles, Kelvin. 312.25 Kelvin divided by 9.34, and this gives me 3.10 atmospheres. Now, where on earth am I going? Oh, we'll erase up the top. So from here, we need to be able to calculate the partial pressure. So the partial pressure, so the pressure of C3H8 is equal to the mole fraction of C3H8 times P total. So that is 0.644 times 3.10, which gives you 1.996, which rounds up to 2.00, because of the sig figs of this value. So this is 2.00 atmospheres. To do the same calculation for argon, so the pressure of argon is equal to chi of argon times P total, which is 0.356 multiplied by 3.10, and that gives you 1.10 atmospheres. And these two totaled together give you P total. So you could have just calculated this row and determined these two values as long as you had the moles of both and knew the total pressure. So I feel like that went quite quickly and we did a lot of stuff. So what questions do you guys have about this? Also, when you're doing your ALEKS, this is very similar to one of your objectives. It will take you a while. You will fill out a table, quite similarly to this, but this should help you orient yourself to that calculation. So what questions do you guys have about this question? Or do you have none? And that's okay too. Are the P total values supposed to be the same? So, Mariah, in this case, the P total is always the same because it is the total pressure of the system. So P total could also be calculated by the sum of either of these values. So they would need to be the same. Like when they add up, do they have to equal what we got from the equation? They should, or be very, very close. So Mariah's question is, like when they add up, do they have to equal what we got from the equation for P total? They should. So your two partial pressures should equal all of the total pressure. Think about it this way. If I make sugar cookies and peppermint cookies, because it's the holidays, the total number of cookies is added up by the number of sugar cookies plus peppermint cookies. So if I were to calculate the fraction of the plate that was sugar cookies, it still should add up to the total value. Good. Any other questions? What time is that? It's 4:03. Whoops. So, it doesn't sound like anyone else has any questions from chapter 10. What's the best way to do this? We'll try it this way. Make it a little bit less busy. And I will not have to wander across. Does anyone have any other questions about any other material that I can answer? If not, that's all I have today. I have office hours on Friday. I will have other office hours also on Monday. I'm available via either one. Email all this weekend while you guys study. If you're like, oh my goodness, I don't remember, I'm happy to try to help you out as we work through this. So what other questions do you guys have today? And if you don't have any, that's okay. You can write none in the comment box, and that'll be it. But I'm excited. It has been my absolute pleasure to work with you guys this semester. I really hope that you guys enjoyed Gen Chem 1. I would have appreciated getting to meet you, but #2020. There's not a lot we can do about that. So I hope you guys have a good rest of your semester. I have no other material prepared today, but if you have questions, you can drop them in the box, and I'm happy to answer them. That's not really working. Any other questions today? It's okay if you don't. But I'll give you guys another 45 seconds or so. Thank you so much. I have had so much fun this semester. I really just had a great time. I miss getting to see you guys in class, but this is the best we can do under the circumstances. Thank you again. It's been great. I hope you guys have a happy holiday season, and finals are going to be over before we know it. Apparently, I use my hands a lot to erase the board. Thank you so much. You guys have been wonderful too. You make this the best. Thanks. Y'all are just going to make me have the best afternoon ever. Y'all, it has been fantastic. Thank you again. I look forward to seeing you. Please stop in my office hours. Someday, supposedly, we'll be back to normal. And y'all, feel free to stop by my office. Or, I guess, find me on Zoom. Who knows? So, y'all have an excellent rest of the day. Happy holidays.